Ce chapitre présente les trois lois de Kepler.
This chapter presents the three Kepler's laws, describing the motion of objects in the solar system, and by extension in every planetary and stellar system. They related in a simple way the masses of the interacting bodies to the shape of their orbit, and to the typical travel times on these orbits, namely the orbital periods. Kepler's laws are the result of the work of a great observer and mathematician. They were deducted from the observations of Danish Tycho Brahe, an astronomer with quite a sturdy character. Strong advocate of the geocentric view of the universe, Tycho Brahe worked from the island of Ven, in front of Copenhagen, that King Frederick II bequeathed to him, to create an observatory, Uraniborg, dedicated to the muse of astronomy. He was the last astronomer before the era of telescopes. He mapped the sky with an extreme precision for the time, using sextants and astrolabes. He even took into account the atmospheric refraction, an apparent displacement of stars on the sky due to the refraction of light rays by the Earth's atmosphere. In 1600, Kepler became Tycho Brahe's assistant, who asked him to compute Mars' orbit. As opposed to Brahe, Kepler supported the model of a heliocentric universe, which was a source of disagreement between them, and slowed down the work of Kepler. His work took him 6 years and was published in 1609. Later, Newton theories built a framework around Kepler's law, which until then only a purely mathematical description of Brahe's observations. Newton's law of gravitation thus became the theory behind the trajectories described by Kepler in the framework of heliocentrism. Note, by the way, that Newton was absolutely not a contemporary of neither Kepler nor Brahe, who therefore worked without any knowledge of the law of gravitation. What do Kepler's laws say? The first one tells us that planets follow flat and elliptical trajectories with the Sun at one of the foci. The second one tells us that the radius vectors sweep out equal areas during equal intervals of time. Finally, the third one, maybe the most important in regard to astrophysics, tells us that the square of the orbital period is proportional to the cube of the semi-major axis of its orbit. Now back to the first Kepler's law. We will not prove here that the orbits are elliptical, but we will quickly show that the orbits are flat. To this end, we will write the angular momentum mv cross r, where v is the velocity vector and r is the radius vector. Let's take the derivatives of this angular momentum with respect to time. We immediately see here the velocity vector. This vector is obviously collinear with itself, and therefore this whole expression vanishes. As we have a radial force, we recognize here the derivative of a momentum with respect to time. We thus have a central force, which is collinear with the radius vector. This means that F being parallel to R, this expression here vanishes. We have then shown that the time derivative of the angular momentum is equal to 0, so L has a constant norm and direction with time. Therefore, the orbit lies on a plane. Kepler's second law tells us that the radius vectors sweep out equal areas during equal intervals of time. Here is a small surface element between two instants. While the Earth moves along its orbit, we have a triangle with its altitude here. We now seek to compute this area. We have here the altitude of the triangle, the radius vector here, Earth's velocity, with a certain angle with respect to the tangent to its orbit. We will call this surface element dA. We then have that dA is equal to the radius vector, which is also the base of the triangle, times half the altitude. Let us express the altitude in terms of known quantities, the velocity. the angle and the time element to travel this small distance along Earth's orbit. We factor out the r divided by 2. The altitude is v dt times the sine of the angle. We immediately see that the norm of the angular momentum, which is mvr sine theta, shows up here to a factor m. We can thus rewrite the surface element in this way. Here is the norm of the angular momentum, which we proved previously to be constant, over 2m times dt. We now simply have to integrate this in order to get the area, which we will express as a function of time. We can derive the value of this constant with the boundary condition that if t equals a full period, then a, t, is the surface of the ellipse, pi, AB. Where a and b are the semi-major, respectively the semi-minor axis. This allows to compute exactly the value of the constant. Between 2 times t1 and t2, we have that a t1 minus a t2 is equal to the norm of the angular momentum over 2m times delta t. Where delta t equals t2 minus t1. We have thus proved the second law. For any t1 and t2, what is important is the value of delta t, namely the time interval between the two observations. We can see this here. If I draw a radius vector here and another one here, the surface swept out by this radius vector must be the same that the one swept out by the radius vectors between the same times t1 and t2. I am here further away on the orbit, so the covered angle will be smaller. Here is a time t2, and the other t2 is here. We have delta t here, and the same delta t here. So the area swept out here is the same one as the area swept out there. This implies that the bodies further away on their orbit are slower. Their tangential speed along their orbit is smaller when further away from the body that attracts them, the Sun in this specific case, than when the Earth here is closer to the Sun. We finally see that the surface A1 here is equal to the surface A2. This is for the second law, Kepler's third law. This law states that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. We will now prove this law in the case of circular orbits. Let us consider a system of two bodies with masses m1 and m2 orbiting around a common center of gravity at distances r1 and r2. The gravitational force that 1 exerts on 2 is, of course, equal to minus the force by 2 on 1. Its value is g m1 m2 over the distance between the two bodies. That is r1 plus r2 squared. This is simply Newton's law. I can multiply this equation by any quantity. I have here multiplied the top and bottom part by the same quantity. I can now rearrange the terms, for example, by grouping these terms here. This term is the total mass of the system. And this is another mass, which we write mu. the reduced mass of the system.
Donc maintenant, dans ces conventions-là,
With these new definitions, the gravitational force is rewritten as
comme G
Gm mu divided by R1 plus R2.
mu sur R1 plus R2, le tout au carré. Où mu va s'appeler la masse réduite.
With mu being the reduced mass.
Dans ces conditions,
This is equivalent to a mass mu orbiting around the mass m
à une distance R1 plus R2, c'est ce
at
qu'on
a
voit
distance of R1 plus R2. This situation is represented here. We have here m1 that orbits at a distance R1 plus R2 around a virtual mass m that would have the total mass of the planetary system. We have thus reduced problem of the motion of two bodies around a common center of gravity to the motion of a body mu with virtual mass mu around another virtual body which has a mass equal to the sum of the masses of the two bodies in a planetary system. The distance between these two virtual bodies is the same as here, R1 plus R2. Let us now consider the acceleration of the mass mu due to mass m in the case of a circular orbit. We call it a mu. It is equal to the angular velocity squared times r1 plus r2. According to Newton's law, it is also equal to Gm divided by r1 plus r2. On the other hand, omega is equal to 2 pi over the orbital period, and we can thus substitute omega here. Omega, mu, and p mu. I therefore get 4 pi divided by p equals Gm divided by R1 plus R2.
Égale à G grand M sur R1 plus R2 au cube. Autrement dit,
in other words, p divided by R1 plus R2 equals 4 pi divided by Gm.
au cube égale à 4 pi 2 sur G grand M. Évidemment,
this is the distance r.
donc dans le cas
in the case where the mass m1 is much larger than m2,
on a simplement que
then the total mass m is approximately m1.
environ la masse M1. Et puis évidemment, le centre de gravité
The center of gravity of the system will be inside m1,
de gravité 2.
almost at the center of m1.
Ici, à voir que,
We have thus that r is approximately equal to r1.
et donc on peut réécrire la loi de Kepler.
We can therefore rewrite this as p divided by r equals 4 pi divided by Gm,
4 pi 2 sur G grand M, qui est la loi qui nous
which is
intéresse.
Kepler's third law.
On remarquera que la troisième
We
loi de
note that
Kepler
this law
ne dépend absolument pas de l'excentricité
does not depend on the eccentricity of the orbit, defined as 1 minus b divided by a, where b, a are the semi-minor, respectively the semi-major axis of the orbit. This means that orbits with different eccentricities
la même période
have the same orbital period as long as the semi-major axis of the orbit
de l'astre principal.
and the mass of the main body are set.
Alors, pour finir, on notera
As a
que si on
final note,
exprime
if we express the semi-major axis of the orbit
en unité astronomique,
in astronomical units, that is 150 millions of kilometers,
évidemment, A égale 1.
and in the case of the Earth, A equals 1, since 150 million of kilometers is the distance from Earth to the Sun, and if the period is expressed in terrestrial years, then P equals 1.
1 aussi.
We have thus renormalized the units
Renormaliser les unités dans la troisième loi de Kepler. On a
of Kepler's
simplement
third
fait
law
une
in such a way that
unité, P2 sur A cube,
P divided by A equals 1 in the appropriate units.
peut être très utile.
This is a very useful relation in the case of the solar system.
Voilà qui clôt notre chapitre sur
This
les
ends our
gravitations.
chapter on Kepler's laws.
De nombreuses
We will meet them many times during this course,
dans
in
la
particular
description de la
in the
forme
description
des queues cométaires,
of the shape of
dans
cometary
l'expression des
tails,
forces de marée qui agissent
in the
sur la
expression
Terre
of
et la
tidal
Lune,
forces acting on the Earth and the Moon, for example, and of course, in a search for exoplanets.